Alright, what is up my homies? Welcome to Brainmelt University. Today we're going to be talking about the OSI and the TCP models. These are two models that are extremely common in information technology, and these are going to be extremely important for you to know whether you're going up for certification, whether you're going to school for IT, or just whether you want to be able to talk the same language as other IT goofballs. As usual, we're going to be talking about the what's, the whys, and the hows. Let's get started. So the OSI model is quite possibly the most commonly referenced term in all of IT. It really doesn't have a lot of basis in fact, but it does help us compartmentalize and visualize just how computers are doing the certain tasks that they are. The OSI model gives us an easier way of visualizing and understanding very complex processes that computers go through in order to perform the tasks that they do. The OSI model consists of 7 layers. From top to bottom, these are the application layer, the presentation layer, the session layer, the transport layer, the network layer, the data link layer, and the physical layer. These layers usually encompass tasks that are performed by a computer. These different tasks help us when we're trying to troubleshoot, whether we're trying to develop new technology, or whether we're trying to just make something work better. By compartmentalizing these different types of concepts and tasks, it gives us a better way of understanding just what we are working with. If you're looking at a way to memorize the different layers of the OSI model, there's 2 different mnemonics that you usually hear. The most common one from top to bottom is all people seem to need data processing. This shows the 7 layers from layer 7 to layer 1. Usually when we're referring to the OSI model, we do start at the top and work our way down, but sometimes you'll see people refer to it from the bottom up. So if you need a mnemonic for that one, I like the mnemonic, please do not throw sausage pizza away. This is a way to memorize your layer 1 through layer 7. So it's 2 different ways of getting the job done. The application layer consists of data that is being actively interfaced with by a human, which means it needs some sort of application to open it, whether that's your web browser, whether that's your Microsoft Word, or whether it's something completely different. Your application layer is pretty much data in creation or data in altering. Your presentation layer, think of it kind of like formatting. Now, 10 years ago, if you tried to open a Word document in a web browser, it just wouldn't work. But with modern web browsers, we have opened them up to be able to read different types of file formats. But as a general rule, if you're working with a docx file, you need Microsoft Word or one of the free equivalents like LibreOffice. If you're trying to open a PDF, you're using something like Foxit, Adobe, or something else. These are the different ways that we format information in a way that the application can present it to us humans in a usable manner. The session layer is more keeping track of how long or what you're doing as you are altering that data. These 3 layers are normally combined by another model we talk about a lot called the TCP IP model, which I'll just refer to as the TCP model for simplification. The TCP IP model is more of a model that's used to represent data in transit. Instead of being called a reference model like the OSI model, the TCP IP model is generally called a protocol model because it shows us how different protocols alter data as it moves from one computer system into another, or how it traverses one network and into another. Both the OSI model and the TCP model, after you look at those combined layers, look very similar. So after the TCP IP model combines the application, presentation, and session layer into one model that it just refers to as application, everything starts to look very similar. Layer 4 of both models is referred to as the transport layer, and both of them are looking at how your computer system is actually going to use it. Think of it like an instruction set for how data must be accessed, how it must be opened, and how it must be interfaced with. Layer 3 of both models, the network layer, refers to how information traverses one network and into another. The network layer is where the internet protocol lives. This is where we are able to have the internet. Without layer 3, the internet would not exist. Layer 2 of both models, the data link layer, allows data to be transmitted across a network. Without layer 2, just networking in general would not function. Layer 2 of the OSI and TCP models, a lot of your physical addressing and other instruction sets used by computers, as well as the timing necessary necessary for them to communicate properly are all handled at layer 2. Layer 1 of both models represents the physical media. It's the physical pieces of hardware that need to get the job done. It's the physical cabling that needs to transmit the power. And if you're wireless networking, it is the electromagnetic waves that are being generated by antennas. So your physical media is how you are able to move information from one computer system to another, or how you're able to store that information once that data is on a computer system. So both models are extremely useful for troubleshooting or just for talking to other IT people to try and communicate where your problems are occurring if you need a helping hand. Both of these models are extremely helpful. Generally in networking, we tend to focus more on the TCP model than the OSI model. That's not to say we don't use the OSI model, but generally the OSI model is a lot more important for people who are working on individual computer systems who need to solve a problem on a specific system versus trying to solve a problem with data in transit. Computer network technicians generally focus a lot more heavily on the TCP model just because it's more simplified, and really we spend the vast majority of our time in layers 2, 3, and 4. And again, this does not mean that layers 5 of the TCP model, the application layer, is not important. We definitely use it, especially when we're looking at cybersecurity and network hardening. But for the most part, we just kind of view the layer 5 as data that is not in transit, and so networking really doesn't focus that much on data that is static. It's looking for data that is moving. Before we get going too far, there is another version of the TCP IP model that floats around in textbooks and on the internet. This is generally referred to as the DOD model, Department of Defense, as they had a hand in developing it. But the 4-layer model is not particularly useful for new technicians who have to memorize both models. The TCP model is very nice because layers 1 through 4 are identical, and the concept of just combining your upper layers 7, 6, and 5 into a single layer is very simple to wrap your head around. The DOD model does not allow for a lot of this because the DOD model, rather than keeping the top condensed and keeping the bottom the same, actually condenses both layers 2 and 1 together. Layer 1 of the DOD model is called the link layer. It encompasses data link and physical together. So now your physical media and the protocols that are communicating across that physical media are now considered one and the same according to the DOD model. Layer 2 is now the representation of layer 3 in the other two models. So the network layers of the other two versions in the DOD model is referred to as the internet layer. Layer 3 of the DOD model is the equivalent of the transport layers, and it actually is referred to as the transport layer, which makes it very difficult to understand whether you're talking about layer 3 transport or layer 4 transport. They're both doing the exact same thing, but the DoD model ends up changing the numbering scheme on you, so it really throws new students for a loop. And finally, we have the top layer, which is generally called application. So layer 4 application, layer 5 application, or layer 7 application. These are all referring to basically the same task, but the DoD model just kind of throws everything out of whack. I generally do not use it when I'm talking to my students, and I usually do not like textbooks that refer to the 4-layer model. The 5-layer is just much simpler. It requires less retraining and less memorization when you can use it hand in hand with the OSI model. We generally tend to use shorthand when we're talking to other technicians, and if you just say, hey, I'm having a layer 3 problem, can you check this out? We generally don't like having to specify I'm having a DoD 3 or I'm having a TCP 3 or I'm having a OSI 3. We generally just say, hey, I'm having a problem with L2, can you help me out? It makes a lot more sense for everyone to be on the same page as to what L2 is referring to without having to increase the length of time it takes to communicate a problem and without creating context problems. Context is a huge issue when it comes to communication, especially in the English language. The less ambiguous your description is, the more likely is that someone can help you or that you can help someone else if they're coming to you with a problem. The TCP model I'm referring to the 5 layer from here on out, because I absolutely hate the DOD model, is a protocol model. Because it's a protocol model, we're generally referring to data in transit because we're networking geeks. So one thing to keep in mind about data in transit is that as data needs to move from one computer system to another, we need to have a way of adding instructions for how that computer system is going to use that data, how they need to respond back to us, and we also need to be able to address that computer system and be able to forward that information to them. If Jack lives in one city and Bob lives in another, we need to be able to forward that information from one city to another. So if you've ever written a physical letter to someone or received physical mail, you know that addresses need to be written in a very specific order so that the post office knows how to deal with them. Your sending addressing and your receiving addressing need to be in very specific areas of that envelope. It is the exact same idea with computer networking. We need to format our information and address it properly, or computer systems just don't know how to handle it. When we're dealing with information at layer 5 of the TCP model, we are generally just referring to data. If you're dealing with cybersecurity, it's generally referred to as a payload. It's something you are attempting to deliver to another computer system. Once that information needs to move out of a computer system and into another, generally the transport layer, layer 4, is attaching instructions for, number 1, how that receiving computer needs to be able to open it, because like I said, you need to have the proper session established, you need to have the proper formatting, and you need to have the proper application to open that specifically formatted information. Without those instruction sets, the receiving computer has no idea how to actually process what it has just received. That's what transport layer does. So it attaches new information to this data or payload, and this is generally called a segment header. Now, if you're using another protocol that also exists at layer 4, UDP, User Datagram Protocol, then it doesn't attach nearly as much information, but it still performs the same basic task. How do you open this information, and what are you going to do with it when you receive it, and how are you going to send information back so I know that this is response traffic? If you're dealing with UDP, this additional information is called a datagram header. If you're dealing with the Transmission Control Protocol, TCP, you are dealing with a segment header. We generally just refer to segment because it'll make what I'm about to say at the end of this little spiel a lot simpler. Once that instruction set has been attached by layer 4, that information goes down to layer 3, where that segment now has additional information attached to it. So a new IP header is added to this information. This information generally includes addressing, so how to get from one computer to another and how to get from one network to another, as well as a lot of other instruction sets that TCP or UDP just either don't care about or that they didn't have room for when they were developing those protocols. This new information is generally referred to as a packet header. When you encapsulate or add that packet header to the existing segment header and to the existing data that's attached to that, this is now referred to as a packet. So whenever you're dealing with packets, you're specifically dealing with information at layer 3. Once that IP information's been added, that packet gets sent down to layer 2, where it not only has a new header attached to it, but it also has a trailer attached to it as well. This new frame header, as it's referred to, includes how that information is going to move from one computer system to another inside that computer network, as well as several other instructions, like what type of a protocol is this going to be using? Is it Ethernet? Are you using an Ethernet cable? Or is it going to be Wi-Fi? Is it going to be traveling across a series of radios? Is it going to be something older, like point-to-point protocol? Or is it something completely different altogether? There are tons of layer 2 protocols out there, and I'm not going to talk about all of them in this video. I could probably do just 2 or 3 videos on nothing but layer 2 protocols, so we're not going to get into those right now. At the end of this information, a frame trailer includes what's called an FCS, frame check sequence. This is an error checking mechanism that allows for information that's been damaged or in some way altered in transit to be thrown away. Computer systems, especially switches and routers that are constantly busy with moving information, do not like processing data that is broken. If it's damaged, that information is basically useless to whoever receives it. So if that frame check sequence fails, it just throws it away. It's not going to bother with it. If it was truly important, something at layer 7 is going to request a retransmit of that information anyway. If it wasn't important, then no harm, no foul. Once this information has completely been encapsulated, so we have our segment encapsulation, we have our packet encapsulation, and we have our frame encapsulation, now we can actually send that across our physical media where it's converted into bits, ones and zeros. These different data structures are referred to as PDUs, protocol data units. This really helps us understand where things are occurring in the TCP model. If I'm referring to a packet, I'm specifically talking about layer 3 information. If I'm talking about a frame, I'm specifically referring to layer 2 information. If you're looking for a nice mnemonic to memorize these PDUs, don't forget to bring your sunscreen, SPF 10. S is your segment, P is your packet, F is your frame, and ones and zeros are your bits. So segment, packet, frame, bits. Don't forget the data though. Datas and payloads are still technically considered a PDU depending on whose textbook you're reading or whose class you're taking. Don't forget the datagrams either, but those only apply if you're using the user datagram protocol instead of the transmission control protocol. So there you have it, guys. That is the TCP, the OSI, and the DOD models. If you have any questions, feel free to drop them in the comments below, and I will see you next time here on Brain Melt University.